Non-deterministic finite automata. The basic idea behind non-determinism is that from any position there are a number of possible computation paths. For automata, non-determinism is manifested as a generalization, the transition relation delta, from a function to a multifunction. Thus, delta now becomes a relation so that from a given state symbol there may be several possibilities for delta of a state symbol. Formally, we have the following definition. Definition 6.4, non-deterministic finite automaton. A non-deterministic finite automaton is a quintuple M equals to K sigma delta SF, where K, SF, and sigma are the same as for a deterministic finite automaton, but delta, which is a subset or equals to the product of K multiplied by sigma multiplied by K, is a relation called the transition relation. Now we can interpret the action of a machine M being in state Qi reading a symbol A as being able to move to any one of the states Qk with the tuple Qi A Qk, which is in delta. Abusing notation slightly, we write Qi A gamma yields in one step to the tuple Qk gamma, but now we will interpret the yield symbol to mean can possibly yield. Again, we will let the yield star denote the reflexive transitive closure of the yield symbol and declare that rho in L of M if and only if Q0 rho yield star of F lambda for some little f in capital F. The interpretation of the definition of a yield star is that we will accept rho provided that there is some way to finish in an accepting state. That is, we will accept rho provided that there is some computation path of M accepting rho. Of course, there may be many computation paths on input rho. Perhaps only one leads to acceptance. Nevertheless, we would accept rho. Example 6.5, we specify M by the following sets. K equals to the set Q0, Q1, Q2, Q3, Q4, Q5, and sigma equals to the set AB, S equals to the set Q0, F equals to the set Q4, and the delta equals to the set of tuples Q0A Q0, Q0B Q0, Q0B Q5, Q5B Q0, Q5A Q1, Q1B Q2, Q1A Q3, Q1B Q4, Q2A Q4, Q2B Q4, Q3B Q4, Q3A Q3, Q4A Q4, Q4B Q4. Note that upon reading, say BABM could finish in states Q0, Q2, Q4, or Q5. The reader should verify that L of M equals to the set rho in the set AB to the star with such that BAB or BA of A AAB is a substring of rho. At first glance, it would appear that non-deterministic automata are much more powerful than deterministic ones. This is not the case, as we see by the classical theorem of Robin and Scott below. We say that the two automata M1 and M2 are equivalent if L of M1 equals to L of M2. Theorem 6.6, Rabin and Scott theorem. Every non-deterministic finite automata is equivalent to a deterministic one. Furthermore, if M is a non-deterministic machine with n states, then we may compute in big O of 2 to the n steps a deterministic machine M prime with at most 2 to the n states. Here the O only depends on the size of the sigma. Prove the construction to follow is often referred to as the subset construction. Let M equals to the tuple K sigma S F delta be a non-deterministic automaton. The idea is quite simple. we will consider the states of the new machine we create from M as corresponding to sets of states from M. We will assume that S equals to the set Q0. Now, on a given symbol A in sigma star, M can go to any of the states Qk with Q0, A, Qk in delta. Let the set Qk1, Qk2, and so on until Qkp list the states with the tuple Q0, A, Q, Kj in delta. The idea is that we will create a state capital Q1 equals to the set Qk1, Qk2, and so on until Qkp, consisting of the set of states of M reachable from Q0 on input A. Consider Q1 for each symbol B in sigma star, and for each qkj in Q1, compute the set dkj of states reachable from qkj via B, and we let Q2 denote the unions of dkj, where the union is taken among all the indexes qkj in Q1. Formally, Q0 equals to S, which is just a set of a singleton Q0. Q1 is the set such that Q in K such that Q0A will yield in one step to Q lambda, and Q2 is the union of the set of all R in K such that QB will yield in one step to R lambda, where the union is taken among all little q in capital Q1. The idea continues inductively as we run through all the members of sigma and the longer input strings. We continue until no new states are generated. Notice that path lengths are bounded by n, which is equals to the size of k, and that the process will halt after big O of 2 to the n steps. The acceptor states of the machine so generated consists of those subsets of K that we construct and contain at least one acceptor state of M. It is routine to prove that this construction works. The algorithm implicit in the proof above is often called Thompson's construction. Notice that we may not necessarily construct all the 2 to the n subsets of K as states. The point here is that many classical proofs of Rabin and Scott's theorem simply say to generate all the 2 to the n subsets of K, then let the initial state of M prime be the set of start states of M. The acceptor states of M prime are the subsets of K containing at least one acceptor state of M, and if F, which is a subset, equals to K, and A, which is in sigma, define the delta of Fa equals to the unions of the set of R in K such that Qa will yield in one step to R lambda, where the union is taken among all little q in capital F. The difference is that the later proof often constructs many useless states, since many of the F, which is a subset equals to K, simply cannot be accepted upon any input string. But no matter what, if we use the later proof, we will indeed take big O of 2 to the n steps. Example 6.7, we apply Thompson's construction to the automaton from example 6.5. The initial state of example 6.5 is Q0 equals to capital Q0 equals to the set of a singleton little q0. We obtain the transition diagram of figure 6.3. Notice that the deterministic automaton generated by Thompson's construction has only 8 states, whereas the worst possible case would be 2 to the 5 equals to 32 states. We remark that it is possible for Thompson's construction, and indeed any construction to generate necessarily omega of 2 to the n states. This is because there exist examples of n states Nondeterministic automata, where any deterministic automata accepting the same strings necessarily need omega up to the n states. We give one example of this phenomena in the next section. Example 6.19. As with the deterministic automata, we can extract the following algorithmic problem. Non-deterministic finite automata acceptance. Input a string row in sigma star, parameter a non-deterministic finite automaton M. Question: does M accept a row? Theorem 6.6 has the following important algorithmic consequence. Corollary 6.8. Non-deterministic finite automata acceptance is big O of n and strongly uniformly FBT. It's very convenient for us to extend the model of a non-deterministic automaton to non-deterministic finite automata with lambda moves. Here one allows spontaneous movement from one state to another with no head movement. Example 6.9. Consider the automaton M given by figure 6.4. For this automaton, on input 110, it is possible for the machine to follow a computation path to any of the four states except Q1. For instance, to get to state Q0, M could read 1 in state Q0, move to state Q1, spontaneously move into state Q2 via the empty transition from Q1 to Q2, travel the 1 transition from Q2 back to Q0, and then finally travel to 0 transition from Q0 to Q0. We invite the reader to check that all the other states are accessible on input 110. Again, it is easy to show that there is no real increase in computational power for the new class of automata. Theorem 6.10. McNaughton and Yamada, Rabin and Scott. Every non-deterministic finite automaton with lambda moves is equivalent to one without lambda moves. Moreover, there is a construction which, when applied to M, a non-deterministic finite automaton with lambda moves and n states, yields an equivalent non-deterministic automaton M prime with big O of n states in a big O of n steps. Proof: let M be a given non-deterministic finite automaton with lambda moves. We construct an equivalent M prime without lambda moves for a state Q of M. Define the equivalence class of Q via E of Q equals to the set of P in K of M such that for OW in sigma star of the following QW yield star of PW. That is, EQ denotes the collection of states accessible from Q with no head movement. In example 6.9, E of Q0 equals to Q0 Q2. As with the proof of theorem 6.6, for M prime we replace states by sets of states of M. This time, the set of states are equivalence classes E of Q for Q in M. Of course, the accepted states are just those E of Q containing accepted states of M, and the new transition on input 8 takes E of Q to E of R, provided that there is some Qi in E of Q and some Qj in E of R with the delta taking Qi to Qj on input A. It is easy to see that this construction works. Exercise 4. When applied to the automaton of example 6.9, the method used in the proof of theorem 6.10 yields the automaton in figure 6.5. Definition 6.11. If L is accepted by a finite automaton over sigma star, we should say that L is finite state over sigma star. We can use these results to establish a number of closure properties for finite state languages. Theorem 6.12. Let fancy L denote the collection of languages accepted by finite automata. Then fancy L is closed under the following: 1. Union. 2. Intersection. 3. Star, i.e. if L is in fancy L, then so is L star, the collection of strings obtainable from L. 4. Complementation. 5. Concatenation, i.e. if L1, L2 is in a fancy L, then so is L1, L2, which is equals to the set of x, y, such that x is in L and y is in x is in L1 and y is in L2. Proof. Let mi equals to ki sigma I si delta I fi such a tuple for I equals to 1, 2 be automata over sigma. By renaming, we can suppose that K1 intersect K2 equals to the empty set. For 1, we simply add a new start state S prime with a lambda move to each of the start states of M1 and M2. The accepted states for M1 union M2 would be F1 union F2. For 4, we need to prove that L of M1 bar is finite state. This is easy. Let M prime equals to the tuple K1 sigma S1 delta 1 K1 minus F1. Clearly, L of M1 bar equals to L of M prime. For 2, we can use the fact that L of M1 intersect L of M2 equals to the bar of L of M1 bar union L of M2 bar. We leave 3 and 5 for the reader exercise 6.